so now we're going to look at a problem, and this is one of those problems where, and I don't know if this is true with women's clothing or not, but I know it always used to amaze me that I'd see these advertisements on TV that would say, you know, buy one suit, get a second suit free, or I guess now it's buy one suit, get 3 suits free. I always wondered how they could afford to stay in business if they're giving away all these suits. And it wasn't until I actually went through the problem that we're about to go through when it suddenly dawned on me. Well, of course, they're not selling suits. They're selling shirts and ties and shoes and belts and everything else, right? So, you know, you can just about give the suit away at cost and still make money if you mark up the shirts and ties and everything else. So that's what we're going to do here. We're going to look at a situation where you've got a company that basically is in the business of selling suits. All right. And every time you sell one suit, you have the opportunity to sell 1.5 ties and 2 shirts. And you'll notice, for example, the price of the suit and the cost of the suit gives you a margin of what? $30. But if you also sell 2 shirts, what's your margin there? 50, right? So if you gave away a suit at cost, you'd now sell 4 shirts, right? See where I'm going with this? Make a lot more money because of the markup on the shirts and ties than you do on the suits alone. All right, so this is problem 7.3 in the textbook, and it's very similar to the problem that we just worked on. We're going to create the demand functions the same way we did before. Now, you'll notice here that we only have one price and one demand value. And as you all know, if you have just one point, you can draw any curve you want, and it'll go through that point, right? But if you read in the textbook, and I was going back because I remembered I had to do this, the textbook tells you ahead of time that you have an elasticity of demand, and the elasticity of demand is estimated to be 2.5. So here is your elasticity of minus 2.5. Now, what does that actually mean? Well, if you remember the problem before, we said demand was equal to some constant times the price raised to the elasticity. T-I-C-I-T-Y. That's right, isn't it? Did I spell that right?
That's awesome.
Oh, does it? Oh. So, yeah, so.
Sure, it's right.
Yeah, I'm not so sure it's right. How about, yeah, I'll just do it this way. E-L-A-S-T-I-C-I-T-Y. That looks right to me. All right. Okay. So if that's our equation, then what we know from the problem statement is 300 is equal to some constant times the current price, which is 350, raised to the elasticity, which is minus 2.5, right? So if we want to solve for the constant, all we have to do is take 300 and divide it by 350 over 2 raised to the 2.5. So I'm going to do that over here. My constant is equal to 300 divided by 350 raised to the minus 2.5. See where that constant comes from now? Okay. So now all we got to do, let's go ahead and start filling in some colors here. All right. We want, first of all, to figure out the price that maximizes profit from suits only. So let's start by, all right, so price is going to be our decision variable. Demand is equal to what? What's the equation for demand? It's the constant times the price raised to the elasticity. And again, it's division by 0 because why? Because the price is 0. So I'm going to put a 1 in there just to get rid of the division by 0 number. How much profit do I make from suits alone? Well, let me set this up as a decision variable for the first go round, or a objective function rather for the first go round. The profit from suits is going to equal to the demand from suits times whatever price I charge minus the unit cost, right? And what I want to do now is I'm going to start using solver. I'm going to do this just like I did the last time. So I want to maximize the profit. I want to do that by changing the price, okay? And I want to add a constraint that said the price has to be greater than or equal to the unit cost. Make decisions non-negative, use my GRG linear, and now let's see what happens. Solver found a solution, okay. It set the price equal to 320, and it set the demand equal to 375.3, and I made 0 profit. Does that look right? How in the world do we get an answer like that? What do you think the problem is? We could do the multi-start. What price did I start with when I was making out when I was building the model? What price did I plug in? 1, right? What if I instead had plugged in a price of, oh, I don't know, let's say 500. All right, and now let's run the solver again and see what happens. Solver converged on a solution. That looks a lot better, doesn't it? What do you think? Should I use a price of 320 or should I use a price of 533? Do you see what happened? This is one of those situations where, yes, we should use the multi-start option. So let's go in to the multi-start option, okay? And now we have to add one more bound, right? So let's put a price, and let's say, again, I don't know about you, but I'm thinking probably nobody's going to pay more than $1,500 for a suit. I don't know, but I'm just going to assume $1,500. So I'll use that as my other bound. And I'm going to click on solve. And guess what? 533.33 is the global optimum. But do you understand what happened to me? because now again, since I'm using multi-start, what if I did put 1 in here again? All right, and now, since I'm using the multi-start option, what happens if I solve? It gets to the 533.33. This is what I was trying to illustrate before, but now you see it happening in front of you. Where you start, if you don't use the multi-start option, could lead you to a local optimum that's not the global optimum. Nonlinear solvers can be a little tricky. Yes?
Can you show us how to set up the multi-start?
Sure. So let's go back in there. All right. So I've got the GRG nonlinear solver selected, first of all. But even if I didn't, when I go to options, you can see there's a tab that says GRG nonlinear. So I click on that tab and I make sure multi-start is checked. Now, it's always good to put bounds on the variable.
How about this number? Because mine is empty. I don't know what kind of number that is.
What this is saying is it's going to choose 100 starting points. All right, that's the population size. And the starting points are going to be determined more or less at random using a procedure where you calculate a random number based on a seed value. And here the seed is 0. So it really doesn't matter what those numbers are. I mean, it matters, but 100 and 0 are as good as any to start with. Okay, well, that's just the profit we make if we're only looking at maximizing profit by selling suits. But we know from the problem statement that for every suit we sell an additional 1.5 ties and 2 shirts. So let's go back now and figure out what profit we make from selling shirts and ties. Well, that's just a very simple calculation, isn't it? We just take the number of suits and multiply it times, in this case, the number of ties times the profit per tie. I take it back. Number of suits times the number of ties. Right? So that gives us the total number of ties that we've sold times the profit per tie plus the shirts times the profit per shirt. Is that equation correct? The equation that I've got says I take the number of suits times the number of ties times the profit per tie. Well, that's right. Plus the number of suits times the number of shirts times the profit per shirt. That looks right. Would you agree? Okay. So our total profit then is equal to the profit from suits plus the profit from shirts and ties. Okay? Now, this is where it's going to get interesting. What if I make this second number, the profit from everything, as my objective, rather than simply the profit from suits? Okay? Remember what we found out before. When we were looking to maximize profit from suits, what we ended up with was 533.33 and 104.7, roughly 105 suits. Okay? How is price per suit going to change when we throw in the additional sources of profit? Well, let's find out. Go back to solver. Now, instead of our objective function being profits from suits, it's going to be the total profit. Okay? We're still going to change the price of the suit. We're still going to have the boundaries that you see here, and we're still going to use the multistart option. Okay? But let's see what happens when we solve it now. Solver converged. And now the price per suit is $412.50. So when we maximize total profits, what we find is we sell the suits for a lot less, right? But we sell almost 199 of them. And the additional 80, well, the additional 94 suits that we sell result in a bunch more ties and shirts at a much higher profit. So we end up much better off by lowering the price of suits. And now you understand why Joseph Banks and Men's Warehouse and even the department stores have these sales where they give away the suits because they're trying to get you to buy the accessories. And I guess this would be a marketing thing. So, what do y'all think of that?
Why didn't you turn the demand into your different sell?
Well, I can, but if I impose the constraint, let me just show you what happens if I impose the constraint that that's an integer. All right. So I'm going to add cell reference has to be an integer. Okay. Integer constraint reference must include only variable cells. In other words, what it's telling me is I can't force a calculated value to be an integer. All right. Now, I could force price to be an integer.
You can charge whatever you want.
Yeah. Yeah. And we could do the same thing we did before. We could let's go ahead and see if we can draw a graph that gives us some kind of economic evaluation here. So let's start at 350 and just go up by 10 each time.
You maybe put the price in a round formula, so they have to get a whole number for that for the demand. Equals round. Put
Well, what I would do is I would do it over here. Oh, I got to give it a 0, don't I? I can't do it in this calculation here. Well, I guess I could. Well, let's try it. Well, yeah, we'll go ahead and try it. Now, keep in mind when I do that, what it's really doing. It's still calculating the 198.9 or whatever was there. It's just displaying 199.
oh, then it doesn't matter at all.
Yeah. So. Okay, so here's
have my table, data, what if, data table. My column input cell is price. Okay. Now insert scatter plot. And there you go. Oops. Okay. It's a very interesting situation. Again, it's a parabola, but you can see that we have quite a change here, right? Just going from 350 to 400, our profit jumps from roughly 30,750 to what looks like 32,750. So our profit really zooms up fast. How many of you are going to really impress your friends tomorrow by explaining why those commercials make sense? Yes, you are going to do that? You're going to. Yes. Yes. Oh, that's easy. The question is, are those discrete values or are those averages? And I would say those are averages. On average, you sell 1.5 ties per suit. You never sell a half tie, right? So sometimes you sell 2 ties, sometimes you sell 1 tie, sometimes you sell 5, sometimes you sell 0. Right? On average, you sell 1.5 ties per suit, and on average, you sell 2 shirts per suit. You can put any numbers in there you want, just use the average demand for the accessory. Make sense? We're going to spend a lot more time dealing with uncertainty when we get to the simulation part of the course. And there you really do need to think very carefully about how those random variables do change. In this case, though, I'm very comfortable saying these represent the mean of a normal distribution. Very good question. Thank you. So now you really feel like you understand this, right? You're going to impress your buddies at work tomorrow, I know. You really. What you need to do is you need to find somebody that's the same size that you are and get them to buy the extra suit. tell them you'll pay them $50 if they'll get extra suits. No, just kidding. Other questions about this problem?